Hello, I hope you enjoy the Distributed SQL Summit. The topic today is transactions in Yugabyte. This is interesting because you can use Yugabyte as a SQL database or as a NoSQL database, and you can choose the level of transaction acidity in both APIs. And it's also important to understand how it works to know that complex SQL transaction may involve more writes than what you can think of. I'm Frank Pachot, I'm developer advocate. If you use Yugabyte, if you have questions, if you have feedback, please contact me. I love to know what you are doing with our open source database. In SQL databases, if you compare with NoSQL, where you read and write documents, in SQL databases, you don't really read and write documents or whatever. You change the database state from one to another. This is what happens when you do any SQL transaction. It changes the state of the database from one to another. And for this, there are a lot of reads and writes happening to table rows, to indexes. Also, log information is there. That can be done sequentially because you run one statement after another, but also in parallel. For example, when you insert in the table that has a secondary index, in parallel, there are writes to the index and writes to the table. But the point is that everything you do must be visible only at a single point in time when you commit. So you can write a lot during the time, but all those writes will be visible only when you commit. Exactly as if you were writing a timestamp with every changes, the version, but this timestamp is the future commit that will happen. And with ACID transactions in SQL, other sessions must read only the state before or the state after, but not the intermediate state while you are reading and writing. Basically, in most databases, they read as of the transaction start time, and they write as of the transaction commit time. I will explain why we have this difference. So we read and write to different states, and then there is conflict resolution if those states conflict. But basically, I start to read, I start my transaction. When I read as of the beginning of the transaction, and I ignore all concurrent writes that are happening, but not yet committed. And when I read as of this point in time. Some databases lock when they read, and then they are able to read the state at the end, but not because they can read in the future, just because they wait that the future becomes present, but this adds latency. Reading from the past is possible on multi-version concurrency control databases. However, when you write, you have no choice. You cannot write a past state because the past is just past. You cannot change the past. So you write by locking, by waiting on locks, you write as of the commit time. To make it more clear, I have an example, but basically, remember that ACID transaction brings the database from one state to another, and those states are identified by the commit time, commit point in time. This is where the changes that happened becomes all visible and durable exactly at the same time atomically. That's the point. The problem is that the timestamp is known only at the end, at commit time, but you write before. So how can you write this timestamp before knowing it? Because the commit time is unknown at the time where you commit, and there are multiple solutions. The databases where reads are blocking writes or waiting on writes, for those that's easy because they just wait until the commit time is known. but of course, this is difficult in OLTP for concurrency. What Yugabyte does, we will see the detail, is staging all writes until the commit time. And then at the commit time, you know the timestamp and the actual writes can happen. But that's more writes, but we will see that there are some optimizations. And the other databases like Postgres or Oracle, what they do, they write directly when you are writing, but they come afterwards to set this timestamp. So it's again additional write amplification in all SQL databases. This will be needed. But I have an example to explain how it works in Yugabyte. So first, virtually, I said that a transaction brings one state to another. So if I have a simple transaction that will update two accounts just because it is transferring money between those two accounts, when I commit, I have the commit time, and this is where the state of the database changes to a new state. Of course, that's virtual. We do not copy the whole database at commit time. So how do we do this in Yugabyte? When you start a transaction, we have a transaction table somewhere. Like other table, it is distributed and replicated for high availability, elasticity, geo distribution, all that. So we store a transaction ID there, no commit time because it is not committed yet. The transaction just started. And then all the changes to rows and columns are not done within the real database, the regular database, but as recorded as provisional records, transaction intents in another small database. So my updates go there. And we don't know the commit time, but we can reference the commit, the transaction information in the transaction table. And this is how another session, when it reads the value for account 10, for example, another session will read the past value. We'll see that there is a new value, but we'll check the commit time. It is not committed, then it's not visible, and it will stay with this value. Okay, and when I commit, the only thing that is done is setting this time to the commit table. And now the concurrent transaction knows that those changes were committed at this specific time, and a transaction that reads as of a time before this will read the past state. A transaction that reads as of a time after this one will know the changes and read the new state. Of course, we cannot stay like that for a long time because then in this transaction table, transaction will accumulate. Once they are committed and once the detail is not needed anymore, this will be cleaned up in the background. User do not wait for that. User waits at commit only to set the commit time. But later in the background, all those will be merged to set directly the new version of the row or the new version of the column value with the commit time. And then MVCC cleanout will happen to remove the intermediate version when they are not needed anymore, but that's another topic. The point here is that when you do something transactional, you may have to stage the changes and then they will be applied later. And I will show an example. I will show also how to trace it if you want to understand exactly how it works for specific statements. Just to compare what other databases do, Oracle does it differently. Rather than staging the changes, it stages the past version into rollback segments. And a cleanout will happen later. It can be done immediately at commits if there are just a few rows, or later the next reads will clean up all that. In Postgres, the same, the next reads will clean up this information. It's not a job that runs asynchronously. It's piggybacked to the next read. And in both databases, you can do a select where you think it's only reading, but actually generating some redo log, some role, because reads can write in those databases. In Yugabyte, it's much simpler. You have this intent DB that states the provisional records, the intents, and they will be applied later to the regular DB asynchronously, but not by the next read, just by a job doing that. Okay, we will look at it, and I will show you how you can trace it. Not for production, the goal is to trace it in a lab, and I've started Yugabyte here with a special parameter to trace all the writes that are happening. And I also disabled the metric snapshotter because it also writes. And you will see that I have enough to read in the logs. I don't want those additional ones. So when this is enabled, in the logs that I will just tail in the background, to see what is happening when I'm interacting with the database, the logs will show the reads and writes. And let's do some SQL statements at that point. I create a database collocated so that I have only one tablet. This will be simpler to read the logs because all those reads and writes are happening for specific tablets. They all have each tablet peer, because they are replicated, have a regular DB and an intent DB to store the provisional records. I create a simple table, cities, where I have a name and a name of a city and a country. I'm not interested by the logs from the create table. I'm interested by the logs when I do something simple. So this is a transaction, a single statement in auto-commit, but it's still a transaction. And we will see that it's not doing what I said. What I said has some optimizations, fast pass in some cases. And here, because my table is very simple, no foreign keys, no secondary indexes. And because I'm inserting only one row in an auto-commit transaction, it doesn't have to write the provisional records because there is only one write and the commit time is known because it is in auto-commit. And then you see that I have written in the background, my single row insert has written 2 key value pairs directly to the regular database, the final database. The 2 key values are, there is one for my colon value, Geneva, the key Geneva has the value Switzerland for the country. So you see the key here and you see the value, but also because I'm inserting a new row, I have an additional right to say this is a new row for this key and an internal information there. And there is the timestamp, the hybrid timestamp, because we are in a distributed cluster. So this is the ideal situation. The write can be done directly to the final database because it was really simple. But if I do something not so simple, where I begin a transaction and I do the same insert, but in a transaction that can do other things, the big difference here is that when I insert, I have to write something, but I don't know when it will be committed. And you see that in the logs, I have a lot more information there. The important thing is that this writes to instance DB, not to the regular DB, to instance, to stage the records. And if you look at it, you will see the values that I've inserted. You see the key, you see somewhere Switzerland for the value of my column. So that's one thing. But there is also some transaction information, transaction metadata, but also a transaction reverse index. The idea is that you cannot have the timestamp directly there. So instead of putting the timestamp, we have a transaction ID. So all the writes reference a transaction ID, but the transaction must also know all the writes that happened in that transaction. And this is why there is a reverse index. So for each write of a new column value, you will see a write in the transaction metadata in this index for this link. Just the most important is to understand that here nothing was written to the regular database, because you cannot write to the regular database before commit, because you do not know the commit timestamp in a complex transaction. But when I commit, there I can see the writes to the regular DB. So the same as before, except that they had to be staged until commit, and the writes to regular DB, but also some writes to the intents. But this is just cleaning the intents DB. You see some deletes. So this is where it looks at this reverse index. This transaction was committed, the committed change was applied to the regular database, and then we go to the transaction metadata. We look at the index to know all the writes that have to be removed. Though this intent database is usually small, it's also stored in a LSM tree like RocksDB, but usually stays in memory because it's really small. I want to show you something else that is quite important. So here we have seen that the database itself, YugabyteDB itself, will decide if it can apply the fast pass, writing directly to regular database, or if it has to provision the records before the commit. There is another case. So this is what I did before. Inserting a single row in a simple table. This was able to be optimized by the fast pass writing to regular DB. But that was also because I had no indexes in it. If I do the same, first I create an index, and you can ignore the logs from the index creation. But now I have an index, a secondary index. The table itself is stored in the primary key, but I have a secondary index there. And now I will do the same, inserting a single row. Before, when no other indexes were involved, this was a single write, bypassing all the provisional records. But now this is already a complex transaction in the sense where it has to atomically write to the table and to the index. And you can see that even inserting a single row in a table that has a secondary index can generate a lot of writes. Don't be afraid that most of those writes are writing in memory at the same place. So this is fast, but a lot of information in intents for the table, for the rows of the table, for the index entries, for the transaction information, updating the reverse index for this, all that. Okay. And that was already committed because this was a single statement in auto commit. So you can also see the cleanup at the end. This is why you see a lot of information. The cleanup happens later. We do not wait on it. Okay, one more thing. So when you are using the SQL API, the Postgres compatible API, Yugabyte will decide if it can use a fast pass writing directly to the regular DB, or if it has to stage the changes to intents DB before. But you can also run complex statements and tell the database, forget about ACID properties. I don't really care. For example, here my table with an index, because it has a secondary index, everything had to go to the provisional records, because if at the same time someone is reading from it, it must see something consistent, not having a different value if it reads from the index or the table. But if you are bulk loading into a database where you have no concurrent reads, then you can tell the database, forget about those ACID properties. I don't care about the transactional rights. You can write directly to the regular DB. If someone can read something that will be eventually consistent, but I don't care. And if I set that and do the same inserts in my table that has an index, to be atomic, to be acid, it had to go to IntenseDB, but here I'm back to something that goes only to regular DB. So 3 key value pairs here, one to say there is a new row, one to say the new value for the column is this one, and one more for the index, because I have a secondary index. This writes to an index. There is a table tablet ID there. And if you look in the UI, for example, you can see the ID. One is for the table, the other is for the index. Okay, that was fast. My goal was just to show you that there is nothing magic. You can trace it. YugabyteDB is optimizing a lot of things, but if you hear about the fast path, it's the way where we can bypass those provisional records in some cases. The most important information we have seen in the logs were the tablet ID, the tablet peer ID, which is the identification of the node that has the tablet replica, because you run with replication factor 3 if you want a fault tolerance. You know how many key values the SQL changes are transformed to key value rights, and you know how many are written to the IntenseDB or the regular DB. So that's the tablet identifier, tablet peer, the rights, regular DB or IntenseDB. And you see the details that mention R or I. I don't know if but you can see it. This is regular DB. And before this was IntenseDB. Okay. And you see some additional rights, but they are close to each other. So in memory, but transaction reverse index, so that the transaction knows which rights have to be cleaned up when they are applied to regular DB. Okay. The important thing is that we kind of solved the problem NoSQL versus SQL. If you use the YSQL API, the Postgres API, you can run complex SQL transactions. Complex, even having a secondary index, you have seen that it's more complex than a single insert. And for those, we have to write provisional records. No database can write only the final value without additional writes. Here, we write to provisional records, but there is a possibility to have a fast pass when it is possible. So when the database knows that it is possible without breaking ACID properties, it will do it. That was the case with my table with no secondary index, for example. But you can also choose to break those ACID properties with a parameter, for example, for bulk load if you are migrating. And this still with the SQL API. You run the SQL syntax, but for a specific statement, you don't need acidity. We have also a Cassandra-like API, so more like NoSQL. And by default, this Cassandra-like API will always use the fast path. So no acid properties. But we have the possibility, even with this Cassandra-like API, to create a table that will be acid, where changes will be acid. And this will go to provisional records. So to summarize, we have two APIs to make it easy to migrate from Cassandra or from SQL database. And in those two APIs, you have the possibility of acid or not. And if it is acid, there are some optimization to run the fast path if it is possible. So you don't have to think really about it. Use the API that you want, define if you use the NoSQL-like API, the default is not acid, but you can enable it. If you use the SQL API, the default is acidity, but you can disable it for specific use case. Think about the consequences. And even if you don't do that, when the database can optimize it, Yugabyte will be able to optimize it. Additional information, this transaction table is itself distributed and replicated. But there is an optimization. You don't want to go to the transaction table in another region if you don't need to. So basically, if your transaction starts to touch data only in the specific region because you did some geo-partitioning, the transaction table that will be used for this transaction will be local. Means that if you touch only one shard, one node, the transaction table will be there with no network calls to look at the transaction status. If the transaction spans multiple nodes, then the transaction table will be distributed to be seen by all other sessions. But this distribution will also try to be in the same zone if you touch data only in the same zone, or in the same region if you touch data only in the same region. This is also a transparent optimization that is done. Usually when you geo-partition, your transaction will touch a specific one for latency reason, and then the transaction table is probably at the same place. If there is a need to have a transaction that touches all regions, then there is a transaction table that is visible by all nodes. Of course, it adds some latency on reads and writes. But the transaction table is distributed. That's a big difference with traditional databases. Traditional databases, when there is a failure, even if they can do a fast failover, all transactions will be rolled back, which has an impact on the throughput, of course. With Yugabyte, when there is a node failure or even a navigability zone failure, new tablet leaders will be elected in the surviving zones or regions. And that also happens for the transaction table. You do not lose the transaction information, the transaction status. You don't have to roll back existing transactions. They can just continue with the replica of the transaction table that has a leader on the surviving zone or region. And of course, with this single transaction table, logically, there are multiple ones because it is replicated. Thanks to that, we have a global acidity. This is very different from sharded databases, for example, like Citus, where they have only local transaction tables and then the reads are not fully acid. Here we are fully acid without the cost of two-phase commit, because we don't have to send the commits to all nodes. We just update the status in a transaction table. And this transaction table is replicated. Everything we have seen there is per tablet. If you distribute by hash or range, each tablet is a Raft group, and those writes are replicated. There is an IntenseDB and a regular DB for each one. So if you write non-transactional writes, go to regular DB directly. If they need to be transactional, they go to IntenseDB and then also update the transaction table. And after the commit, this transaction table is updated and the intents go to regular DB. And when you read from all of them. This looks like reading a lot, but the same happens in all databases. If you read from Oracle, you may have to read also from the rollback segment. If you read from Postgres, you may have to read the past version as well. But each one is optimized because you read for a specific key in each of them. Okay, that was all. Thank you very much. If you have questions, do not hesitate. I'm easy to find on LinkedIn, Twitter, whatever. And we have a community Slack, we have GitHub, and all feedback is welcome. Thank you very much.